Okay, can you see my screen?
Yes.
Okay. Good afternoon, everyone. Thanks for this opportunity. I'm very grateful and honored to have this opportunity to deliver a presentation here. My name is Zhengfang WANG. I'm from Shandong University. The title of my talk today is Deep Learning-Based Ground Penetrating Radar Interpretation and Internal Structure Defects Intelligence Inspection. My talk includes 5 parts. I'm going to start with a background and motivation. In recent years, a large number of tunnels has been constructed and operated, especially in China. During the operation period of those tunnels, the structural defects affect the safe operation of the tunnels. Some of the defects, such as cracks, spalling, can be seen visually, which is called the surface defects, while some of them cannot be seen from outside, like the holes, the separation, or void. This is called the subsurface defects or internal defects. This slide shows some accidents caused by the structural defects during the operation of tunnel. Some of the examples, like the collapse of Sasuke Tunnel in Japan, the block falling of Boston Tunnel in the United States. Those accidents also happens in China. Inspection and diagnosis of the tunnel structure defects should be a priority for safety and economic reasons. Compared with the traditional inspection method, which is labor-intensive and time-consuming, the automatic inspection and diagnosis are expected to replace the human work and have received considerable interest in recent years. So in this talk, I will introduce some development regarding tunnel structure defect intelligence inspection technologies. Then I will move to the second part to tell you something about the robotic inspection system. In order to realize the automatic inspection of the tunnel line, one issue should be solved is how to automatically manipulate the GPR. Due to the complex surface of the tunnel and the inevitable bending on the routing, usually the GPR cannot properly attach on the surface and automatically scan along the surface. So it's difficult for us to collect the high quality data. In order to solve this issue, we developed the robotics inspection system. I will first introduce some fundamentals of GPR. GPR stands for ground penetrating radar. It's not ultrasonic radar, not LiDAR, not INSAR, not STAR. It's widely used for non-destructive detection techniques for the subsurface defects. The GPR usually has a transmitter and a receiver. It transmits a high frequency electromagnetic waves to penetrate through the subsurface structure. The wave transmit at different media has different speed, which is presented by dielectric. When the signal returned to the antenna, we recorded a two-way travel time and the amplitude of the signal to form a B-scan like this finger. Then from this B-scan, we can interpret what is the defects and where is the defects. Also, we can reconstruct the dielectric distribution of the structure to be detected. Then we have developed our own GPR device. It is a compact GPR device, integrated control unit and the antennas. This guy can be equipped on robot arms for automatic inspection. We utilize the robotic arm to manipulate the GPR to scan along the tunnel surface without obstruction. The key technology is we have developed an adaptive control method to adjust the distance between the GPR and the scanned surface based on the information collected by the multiple laser displacement sensors. Then the system can adaptively adjust the GPR for the surface with complex shapes and for the routing with complex curves. We have developed the tunnel inspection robot, which was equipped with a GPR and a linear scanning camera for automatic inspection of the surface and internal defects being applied. Then I will some I will introduce the dielectric property inversion. As we can see from the figure, that the GPR collected reflected electromagnetic signals rather than the actual shape of the defects. So the reflected echoes are not specially aligned to its actual shapes. So the problem need to resolved is how to reconstruct the dielectric distribution, or we call it the permittivity value distribution from the GPR data. In order to solve this issue, we developed some deep learning-based dielectric property inversion methods. Firstly, we developed a deep learning-based inversion method and designed a new deep neural network. We call it the GPR-Invernet for permittivity distribution reconstruction and complex defects imaging from the GPR data. Specifically, we designed a trace-to-trace encoder to enhance the feature of each GPI trace using the information from its adjacent traces and form what we call an enhanced trace. With this enhanced trace, the relative permittivity that is specially aligned to the enhanced traces was accurately reconstructed. The simulation validation result demonstrates that our method can accurately reconstruct the shapes of the defects and rebar with the clear boundaries. Then, as we know that GPR usually move along the tunnel when performing the inspection, then collects data of long survey line. The existing method is divided these data into several segments and use a DNA model to process each segment separately and then splice the result. This may lead to the distorted shapes and inconstant dielectric value in the splice area of the two segments like this. So in order to solve this issue, we proposed a multitask deep neural network that combines CNN with LSTM for permittivity inversion of continuous GPR data collected from a long service line. Specifically, we use a dense unit and bi-convex LSTM to share and fuse information of the several bit-scan segments. Then during the decoder, we designed a dual task decoder for simultaneously invert the permittivity distribution and provide us the class label of the defect. Then the simulation results demonstrate that the distortion of defects, the defect's shape and the inconsistency of permittivity value was mitigated, and the defects category and permittivity distribution was obtained. In order to validate the aforementioned method, we built a concrete model, and we deployed some artifact defects in the concrete model to simulate the so-called defects. The result demonstrated that the method can reconstruct the shape of amorphity and the dielectric distribution of the concrete for both water and air defects. We also built a sandbox model that containing artifacts defects for validation. The method has retrieved its final result and provide us the permittivity inversion result and the imaging of the defects. Then I will go to the fourth part. Honestly, the dielectric inversion is more for like the academic uses purpose. But in industry, all we need to know is where is the location, where is the location of the defects and what the location is. So the issue is how to identify the class label and the location of the defects from the GPR image. To solve this issue, we started the deep learning-based subsurface defects identification method. So the challenge is currently there isn't available data set for the GPR image, not like the image, the neutral net image collected by the camera. As an annotation of the GPR image is time consuming. More importantly, annotated GPR image in one tunnel may not be applicable to other tunnels. So the issue is how we can identify the inner defects when the annotated GPR image are unavailable. So we designed a two-stage method. The first stage, we use the unsupervised actual to cynetic GPR image translation work for precision and generate a translated cynetic GPR image. And then in the second stage, we use the DN model, which is trained only on the cynetic GPR image for identification.
Professor Wang, 3 minutes left.
Okay.
Thank you.
To be specific, for the unsupervised GPR image translation network, it is trained using unpaired actual and cynetic GPR data in an unsupervised manner. And this guy can convert the GPR image collected in real world to the corresponding cynetic GPR image. Then the translated cynetic GPR image retains the characteristics of the defects and keep the style of simulated data. This is followed by a DN model with a deformable convolutional kernel and a rotational region detection module to identify the category and location of arbitrary oriented defects. The key is we used a deformable convolutional kernel for feature extraction. It can adaptively change the shape of the convolutional kernel according to the shape of the defects, not like the the traditional kernel, which has the fixed shapes. The simulation result demonstrates that not only the category and location, but also the orientation of the arbitrary oriented defects can be detected. Then the method was also tested by the sandbox model, and it can provide us the location and orientation, and as well as the class label of the defects. And the field testing was performed in several tunnels. The categories, accurate location of the arbitrary oriented defects was identified. These are some results. To conclusion, we have developed a compact GPR and tunnel inspection robot for automatic tunnel detection. And some deep learning based GPR data inversion method was introduced for tunnel structure defects imaging and dielectric property inversion. And GPR image based some subsurface defects intelligent identification method was designed for providing the class label of defects and the location of arbitrary oriented defects when annotated GPR image are available. That's all for my talk today. Thanks very much for your attention. Thank you.